Good afternoon. I want to talk about concept-based testing. I hope it's interesting. My name is Dietmar Kühl. I work for Bloomberg. One thing I want to shout out first: if you have a question, just shout it out. It's way easier than getting back in the end, I think. Yeah. So my plan to talk about is, first off, I will give a slight vision on where I want to go towards the end of the talk. And then I do an entire detour talking about concepts as they come in C++20, followed by how to do something similar to concepts as much as it's needed for the testing I'm envisioning using the detection idiom. Actually, Marshall talked about the detection idiom last year over here, but I still talk about it again because I found that people still don't know about it or don't get how it's used, and admittedly, when I haven't used it for a few weeks, then I have to look it up as well. So, and then I talk a little bit about the stuff I actually want to talk about, generic tests, followed by a little short demo to see that actually it does kind of work. The idea does work. It's not fully done or anything, but still. Okay, so my vision is actually, at the moment when you write code, I hope everybody is testing things. However, when writing things like, let's say you write a container and you create an iterator for that, and you have created your own container for whatever reason before, you find that the container tests, the iterator tests look a lot very similar. Like the way you test that, oh, you can go to the next iterator with both pre and post increment, that's just the same stuff. So you go and cut and paste code from one thing to another, and I hate code duplication. Cut and paste is the worst thing for development because people often go, oh, right, I just cut and paste that code, and then you have multiple copies, nothing gets updated. Same applies to tests. So the idea is, then quite a number of tests and concepts, I think, promote that, where you basically have classes, you need to test them, and you test, roughly speaking, the same thing, because it still follows the same concept. It's still the same things around. And that's the entire idea. And so you would still need to do some custom tests. Your iterator or your container certainly have some specific behavior, otherwise you wouldn't implement it. That cannot be generic, but some generic stuff can be leveraged out. So here's a simple example. Let's say I've written a class X, and I want or need to have it a comparison operator. Sure, I know with C++20, operator starship may make that all very easy and nice, but that doesn't exist, and it's a nice enough example to show what I'm after. I actually want to write a test. Here's a simple test driver for the class, which just tests the thing. And I want to write test EqualityComparable, and then I give it a number of specimens. Basically, I just say, all right, create some instances of that class. That should be easy enough, I imagine. It's way easier than writing the actual test. And then it should figure out that the code is correct or not. And well, actually, this code is not correct. So even a simple mistake, you can go, well, we know how to write these functions. It's easy enough. But we may make simple mistakes, so having the test is useful, and it would discover that. This is what I'm after. So all in all, instead of spending time on individual tests for every class and always rethinking what do I need to test to be for things to be whatever, equality comparable, less than comparable, all of that, I would like to spend that time once and then reuse things multiple times. So somebody comes up with actually comprehensive tests for the corresponding concept, and everybody benefits from that being done. If everything goes really well, and I can convince this crowd over here, and they convince more people, and then you should enforce that the standard libraries actually ship this test for at least standard concepts. That would be really awesome, right? You just get a library and you go, all right, I need to write an iterator or an equality operator, and you just use something from the library to test that code. I think that would be pretty cool. The assumption over there is a little bit that actually you have some things which are common across multiple developers. If everybody does their own thing, you won't be able to share that, but concepts is trying to go in that direction. So let's talk a little bit about concepts. The idea of concepts is nothing new. It exists since the original version of the standard. It wasn't called concepts back then. Back then it was actually called requirements, although the idea of concepts was already there. Nowadays we call these guys concepts, and it's basically just an abstraction saying we have a similar behavior. There's some support coming with C++ 2x or C++ 20, hopefully, where the support is basically you can express what syntax is required from the from classes modeling the corresponding concept. A concept, this is fairly important, consists of both syntax, this is how you express operations, as well as semantics, which are associated with these operations. So it's not just the syntax. The support which gets into C++ 20 will only be checking syntax. You can say, does this guy follow that concept? And it checks, oh, it has these corresponding operators. It has no way really to detect that the semantics are right. So even with C++ 20, the stuff I'm going to present makes sense because the semantic constraints are still relevant and have to be checked. This is basically what's normally referred to as axioms or the semantics of things. They could in theory be expressed to some extent, but whether they could be tested based on whatever is expressed is yet another question. So looking at an example, this is roughly speaking what one of the, it's a little bit simplified, the real equality comparison which goes into the standard is probably is based on a heterogeneous implementation where you can have A and B, have different types. This is just a little bit simplified, but in spirit, this is one of the concepts. The way to define it is you basically say, right, template, type name T, and then concept. And what that effectively is, it's a Boolean predicate you can use at compile time. And the Boolean predicate, all that really is, it consists of a list of Boolean conditions. In this case, it's just one condition, the requires clause. And then the other part of the description, this is the syntax. The top part is what the standard supports, is expressing the syntax of the thing. There's a little bit dependencies, and I will talk about that more concretely. And then there's an associated set of axioms which basically define what does that actually mean. And equality comparable, well, it means, okay, the thing is reflexive, it's transitive, and, symmetric first, and then transitive. These are basically logical predicates for equality. So you want to define, make sure that holds. Okay, taking that away, this is the concept definition. A use could look like that. We basically say you want to constrain a function f to accept only types which are equality comparable. So basically just say template and requires, this is the new syntax you can use followed by a normal template declaration. Now people went and said, well, that gets often very verbose and it would be nice if we could make that slightly shorter. So there's this is just a name. So there's an alternative notation. This notation and this notation is entirely equivalent. It basically just says, over here we express instead of type name, why repeat that unnecessarily equality comparable. And the argument actually gets into the first argument. You can have more arguments, which then looks a little bit odd sometimes, because you may have 3 concept arguments and you define something which has types already specified in the other, and then this gets in the first. But I don't want to talk about any of that because this is expressing how they're used, and that doesn't work until C++ 20. Some people say this is still a lot of clutter, and we actually should write it like that. So it's basically, let's write a function and we just stick the concept name in there. There's quite a bit of contention about that idea. Some people say this is absolutely the only and right way to do it. And other people say this is absolutely not viable because function templates behave entirely different to non-functions, and you would actually need to know whether equality comparable happens to be a concept or not. For that guy, we probably know that, and there's probably a couple of small concepts we know about, but once you get out of that, who knows? You see a function, you're trying to debug something in a rush, you have no idea what's going to happen. So as a result, at the moment, we don't have a short notation like that. Something in that space probably comes The people who say, all right, this is not acceptable, would be happy with, or would consider it acceptable to have, or most of those, as far as I can tell, some hint of something in there. The people who think this is the right notation go, no, this is the right notation, period. So also a little bit of a problem. Talking about the concept definitions. The concept definition over here is actually, this is, before we saw a requires clause, there's also a requires expression. You can actually write requires expressions in the requires clause, which basically says you may end up with beautiful syntax saying template F requires, and then saying we're kind of cool with that. We also write long. And if you get a longer in, we write long maybe, who knows? But whatever, this is just syntax, and if it is really not bearable, we can find a different way how to do that. The key idea of the requires expression is, inside the requires expression itself is a constexpr Boolean thing. It gives you a true or false value, which is false as soon as anything inside doesn't really quite work. And there's a special syntax to define a number of variations on how the requires clause can be expressed. So let's talk a little bit about that. The simplest way to do things is you can just write a simple requirement, which is literally just an expression. You just write an expression, semicolon, and what that means is this expression makes sense for the corresponding types of A and B. So if A and B, if there's a plus operator, whatever it returns, we don't care about any of that. If that, the compiler knows what that is, this is okay. If anything in there is not okay, the result, the compiler doesn't fail. It just says, no, this requires is not met, it returns false. That's a little bit more complicated, and I will go a little bit more about details. There's a compound requirement where you write things in curlies, and then you can specify whether it's no except or has specific properties of the return type, because often you want to know that, well, operator plus is supposed to return something which is maybe copyable or whatever it is. You can write these guys in there. You can have a type requirement, which literally says type name tinner or type name whatever you write is valid. And then there's a slightly kind of weird nested requirement where you can say requires, and then you can figure out properties about the type. So just this guy is literally very simple. The requires expression, the parameters, you can actually specify things like constref and not constref, so that you basically can nail down the types of A and B. So if you only require a quality operator to work on on const objects, then you can write like so. If you require that a non-const L value for something, you leave the const out, and it would work if the type is a const and all that. So it's relatively cool. The top one where it says where it looks as if we pass these values by value, it does not require a copy or move constructor. All that says is we have a non-const t and we operate on that. It's literally just syntax. It's not like function declarations where there are any implicit requirements. Then something like a type requirement, if we know the type t, we can also leave the parameters out because we don't need to refer to any values. There's no need to declare any of that. We can declare them, it doesn't matter, but we can leave it out. And then say type name t : value type, if that exists, that's fine. Or type name value type t, if that is somehow exists or doesn't exist, depending on type t. And what that has is, I think, whether it's not just whether value type t is actually kind of a thing, but possibly whether it's defined a complete type or something like that. So there's a number of things that checks. Way more interesting is the compound requirements, which come, well, the simplest compound requirement is actually very much like a simple requirement. You just write things in curlies, and it has exactly the same semantics as the simple requirement without the curlies. Okay. You can also write arrow and then say, okay, the result of this expression is something which is convertible, implicitly convertible to the type. So if A equals B returns a pointer, for example, that's perfectly fine. It doesn't have to be the same type for the bool because pointers convert to bool. That's okay. You can make it very concrete to say, all right, A equals B actually have to be the same type as what comes out. So the last example says it really has to return bool. If it does not return bool, if it returns a fancy bool or something which is convertible to bool, this is not acceptable in that context. And then the other one with no except says detects whether the expression inside the curlies is known to be no except. So all the operations, whatever you write in that expression, in this case it's just the equality operator, but everything inside it has to be no except to say, yeah, this is true. So you can check some constraints so you know, well, for example, the no except stuff could be useful to say, right, I don't deal with exceptions in my code for whatever reason, and I check that the arguments passed in really also don't throw exceptions, and otherwise it will be compile error. Okay. Then nested requirement is something where you basically say requires A, and then you can use type properties like requires 4 is less than size of A. So A cannot be evaluated because that would be a runtime thingy, but you can find out about properties. So it's basically like in any non-evaluated context, you can stick in a size of or something, but something like 4 is less than A, that does not work. Okay, cool. Now, concepts will unfortunately not be available before C++20. Hopefully they become available with C++20, but it's still a few years to go, and I would like to do these things now. And and concepts are actually in the standard since a long time. I just didn't get the idea before that we could do something fancy before. So for the purpose of generic tests, we don't really care about a lot of the functionality. All we really need to know is whether they can detect types or detect expressions. And then we could basically go, right, this expression is there, and we say yes or no. And for some of the things, it may actually be acceptable for tests to be more involved than concept use. So you may write a little bit extra clutter and syntax because you just do it once and then everybody's using it. So it's should be kind of okay. It's maybe not nice, but once you have concepts, you may be able to write things easier. But we don't. So let's simulate some of the concept stuff. And the main problem over there is, or the main thing which is relatively recent revelation is that you can quite easily detect the existence of operations, not just of types. Everybody knows how to detect types, right, I guess. So you basically use Finney, and you just use a nested type, and if that type is not there, it's not there, and you can use a nabblef to detect all of that, and that's fairly easy. And the idea over here is to basically say, all right, if I want to detect whether an operation is available, I just construct an expression of that, and I detect whether I can determine the type of that expression. So I basically resolve the idea of is an operation available back to is a type available. So let's see how that could work. Let's say we want to implement a simple requirement, and we have this requires. We could actually, well, first off, span it a little bit out so I can have a little bit space to plunk a little bit syntax in. And now let's rewrite that. So the arguments in the top, we could actually quite easily get rid of the values and replace them by something we have readily available, decval of S and decval of T. It's non-evaluated context. It's all fine. This basically produces exactly the types S and T. So the next step would be to say, well, we can determine the type of that. That's really easy. We just stick a decal type in front of that. And now we give it a name. For example, using equality is, so equality is the type of this expression. And then the require stuff over there, we don't really need much of that because we can actually write type name S and T. And now we have simulated pretty much, we get the type of the expression that requires clause expected. We want to do a little bit of sanity for that. Equality, most of the time we don't want to, or often we want to determine whether equality is available between two of the same types. We actually change the alias a little bit and stick that one in. And for a little bit more sanity, this is really nice when you have multiple requires and you don't know how many arguments is. You just, for good measure, you put a variety template argument at the end of that. And this just sits there and is pretty much ignored. Now, With this using lies, we could have basically a name for something where we can detect an operation. So by basically saying, if the type of equality for the corresponding type exists, the operation exists. Yes?
Excuse me, could you repeat why you put the type name, at the end?
Okay. Okay, so for the actual detection idiom, you don't need that.
Okay.
However, I found it quite useful to say you detect things and you basically generically detect multiple properties. So you put your template arguments in a specific order, and some of the properties you want to detect actually take more arguments. So you basically say detect, and you have a generic detector and I stick in these 4 template parameters, and they're just detected for some of these guys it doesn't matter, and in other cases where it matters, it picks them up from there. So this is basically just a generic way to phrase the requirement and then later not care much about the number of arguments. Okay? So if we have that, we have a way to detect a type exists if an operation exists. So the next step is we just need to build a little bit of facility around that and use it to bundle it up. And the idea over there is actually what the detection idiom is. We basically detect available syntax based on whether the type of an expression can be produced. So we would like to write something in the bottom, the equality we just wrote, and we want to write something like is detected v of equality of t, to say equality for t does exist. This is not quite just a requires of a concept or the concept equality, but it's reasonably close, and maybe with a little bit of macro we can make it even closer. So the real question is how do we implement is detected v, and for that we implement detect. So let's implement detect. Detect is a slightly weird template, taking lots of parameters, and some of them are weird. So the first thing is we stick in an operation and a list of arguments. This is basically this operation instantiated with these arguments or used with these arguments, does it exist? This is what op and the list of arguments is. And we define a default version which basically says it's false. We pretend it does not exist. There's a slight nicety over here, the using type t. If we actually do define a type all the time, it allows us later to deal in types when we use it and we need a type. For example, we want to check whether the type is the same as another type. We could just say, is it the same as the other one? And we just need to make sure that the type we test against, the default type we use, is something which is definitely different from the type we expect. And we're done. So this is why we also define a type. It's just a nice trick. And then there's one template argument, this type name over there, which we don't name and which we don't really use over here. And this is the only use of that is to specialize on. It's the only use of this template. Because what we do next is we basically go and say we define a specialization. And we define a specialization which takes void t of operator args. So this guy over here, this type, exists if the operator exists on the arguments. And if so, we create the void t of that. And then we basically just go over here and say, well, the other things are not specialized, we just pass them on. And the argument we take over here, because this exists, we can formulate that actually, is we give it the type which is the return type of that operation. That's really easy. So all the magic is in the void t. So void t must be really complicated. Here it is. It's a template argument, template taking arbitrary number of arguments and always returning void. This is slightly surprising, but it actually does do the trick. Over here, we actually use void t just with one argument, because this is this is all we need over here. But defining void t for ... is a nice way to do the same trick, not just with one operation, but with a whole set of operations. You can basically conjunction of all the operations. Do all these operations exist, and you just list them, and you get one void t back if you want to. So, and now we just need to wrap it up. Because we specialized on void, we know the template argument which goes into the void position In the first position, we just define a type, non-such, which we only use for this purpose to sit here. So we have a type we can safely compare against, to say this is not the type we want. And then we just take the operator A and B in. So isDetected takes 2 arguments, and it's basically the operation and the arguments. And then we just package it up into isDetected V, which gets a value out of that. Because we derive from false type and true type, there's a value inside, so we can pull it out. And detected T, and so this is not a using alias, this is actually an inline const expression. Inline const expression, really useful. It's basically defining a global variable in every translation unit to include that thing in. But because this const expression is kind of okay, because this variable is not really that variable, it doesn't actually change. And then detected T gives us the type of the expression. So we get both a very easy test, does this expression exist, plus a very nice a simple way to figure out what is the type, or to get a type, which is if it doesn't exist. So we don't necessarily have to do conditional compilation if we just need the type for something. So this is all the detected idiom. With that, we can simulate most of the requires clauses quite easily. So the idea is basically detect whether the availability declaration exists. It yields compile time checks. It does work with C++11, except that you need an implementation of void T, but that is not that hard to do. So void T is actually in C++17. So somebody sneaked that in. So to simulate things, a relatively naive variation is a simple requirement. We basically replace that by basically just a decal type and together, so we need to write that, plus an isDetected V. Just before the presentation, Richard Smith told me that, oh, there's actually a really nice way you can use a generic lambda to simulate that. You basically do roughly the same expression, but instead of using these names, you actually in the generic lambda, you have auto A, auto B, so you don't need to fuff about with decal val, and you use just a return type. You use a return with decal type, and inside you just return the expression you're interested in, and then you need to package that a little bit up. That may make it even easier and on the fly. So but even that is not that bad. What I dislike about this test itself is that you have to have one place where you define the actual expressions, and you have a use place where you actually need to have them available. And with the lambda thing, it may be possible to do that in just one go.
So
yes?
only in 14 as well, right?
Sorry?
Generic lambdas
yeah, generic lambdas would only work with C++14, but whereas this would work with C++11, but that's okay, right? We have all moved off C++14 and moved C++17 even, so who cares about 11? I just claim that for a moment. Okay, so this is a simple requirement. And type requirement, we don't really need much of that anyway, but we could write it as isDetected V, and we just write the type there. That just readily works. What's slightly more interesting is a compound requirement. There are multiple variations of that. If you basically have the simple version where you specify the type, you would simulate it by using isConvertible V with the detected type of T. And over here is, for example, very convenient that the detected type of T is always available, even if the expression doesn't exist, because it will be a type which does not convert to bool. That's fine. This is all what is needed. So you have something which is not convertible, even though a type exists, but you don't have to do conditional compilation around that, which would make it somewhat more annoying. So isConvertible is one of the type traits. The V version, again, Richard might want to point out that it's only available with C++14, not with C++11, maybe even only with 17, I don't know. But everybody uses them, I think. So if you have a compound requirement where we actually check a concept, now, when I say we check a concept, that's a little bit weird. If we don't have concepts, how can we check against a concept? Now concepts are just Boolean expressions. So we could actually define something like a concept using const expression bool. Same, in this case, all it is just uses a same v of the type. This is pretty much simulating the same concept, which says, right, the two arguments are the same. And then to detect whether this guy is met, we actually again use detect t, which is the always available type for the operation we have, and check whether it happens to be bool. So that's fairly easy to simulate as well. There's nearly, or much of the concept side, much of the concepts needed for the testing actually. And I think you can build most of what concepts do with that. It's slightly more awkward syntax. There's some things which concepts will bring you cannot really simulate with that. One of the things is you cannot really do concept overloading. In C++20, there will be availability of concept overloading. With an open set, you can still overload on concepts by just testing and having conditionals. But in C++20, you could actually add new concepts, and then there's basically partial overloading on concept specifications. Okay, so nested requirements, I didn't put that onto slides, it just gets messy. And I think they're rarely used. At least I expect them to be relatively rarely used. I'm sure some power users will always use them, but the power users can also figure out how to simulate them, and they can be simulated. It's just more messy. There's nothing actually in there, which is fundamentally not doable. Okay, then the other side, this is not really needed for the testing, but we could actually simulate constrained templates based on that. Mostly. There are some things which are really hard to constrain, and that's not, you can still simulate it, but it's not that easy. But for many things, it's fairly easy to constrain classes. Let's say we have something like template equality comparable of t, class example. This would be the concept world, and we can pretty much simulate that by basically saying type name t, and then over here we have an unnamed type name and defaulted type name, which is just void t of equal t. Now, the trick over here is, if this form cannot be produced, the entire class declaration doesn't exist for that type, so it just goes away. That's really all that's needed. And then you would just write the template, and if this is not met, the compiler says it does not exist. You cannot specialize it. So it's really easy to simulate. Similarly for functions, you just stick that at the end. And again, the template declaration would work out, oh, I cannot do that, so I cannot have that overload. This does not cover all the cases. For both of these things, for example, if you have a variadic argument list, you cannot stick a default parameter at the end, because there's nothing coming after a variadic list. So if you have a variadic argument list, you need to do something else. For example, the easy way for functions, for normal functions at least, would be use Finney on the return type. So there's something which can be done there. It becomes more harder if you have functions which do not have a return type, like constructors. Over there, you actually need to fluff about, and some of these things, as Richard stated, that he can do nearly all of the things, but some of the things are fairly hard to do, and you do base classes where you define things, and then things get deleted or not deleted, and it's messy. For most of the easy things, this is all which is needed for constraining templates. Again, concepts will solve all of that. You can constrain all the concept, all the functions, all the operations with concepts. So, back to the actual idea, and that is concept-based testing. Concepts consist of syntax and semantics, so we can actually write some of the requires expressions with is detected, and once we have detected operations, we can then go and write actual semantic tests. The idea would be you have conditional operations on that. And then the generic behavior applies to everything, so we can just, it makes sense to test the generic semantics. And well, and that will actually remain, particularly that part. because the C++ 20 concepts have no idea of formally specifying the semantics. And I guess this will kind of remain, because whatever you test, you probably need some objects to work on. And over here in the test, you could just say, oh, give me 3 objects of that type. And then you do some operations on these 3 objects to figure things out. Whereas a compiler has possibly no way to actually conjure that up and know what the results would be. One of the things which I want, at least for from these tests, is when starting to write an iterator, for example, I would like that I compile and it tells me, all right, this operation is already working, that's okay, but these operations are missing. And maybe we go even fancy, and if I have some operations and we have ideas how they're generically implemented, the report could even say, oh, and you could implement that like that. So I think that would be really nice if a user says, all right, just write an iterator and you start with an empty class, you compile, and it tells you, oh, these things, the test tells me are not there. Then you implement them and says, yeah, not that way. You actually need to implement them differently. That's a problem over there. And I will do a bit of a demo of that later. And so we basically would use if constexpr, for example, to detect, is an operation available? And if it is available, we can semantically test it. Yeah, I think I pretty much walked over that. Is incomplete models, incompletely modeling things is a thing. There's also some people in a previous version when I did that said, well, we sometimes implement an iterator, but we don't implement all the operations because I just want to use copy, and copy doesn't need any of these operations. So I just implemented whatever the increment operator or the pre-increment operator, and I never bothered to write the post-increment operator, and it never uses inequality or whatever it doesn't use. I'm not a fan of that, and these tests will provide reports. It's entirely conceivable that if these tests are packaged up in a test environment, that you basically could specify ignore these tests readily, but this is box standard work. What people may or may not do with other unit tests, where unit tests fail, they may say, all right, well, disable that test for now, and we just ignore that. This is entirely outside, can be done. Personally, I think it should be complete, and this is what I'm aiming for. So we have seen that this is equality comparable, has these semantic requirements. So let's walk through how to test some of that. I won't show all of that because it does get somewhat messy to actually do it. But, well, this is what tests often are. They're often kind of somewhat of a mess where you basically try to work things out. So the first thing to define is equality operations. There are 2, equality and inequality. So we just define those to have names for our tests. That is relatively straightforward, so equality, inequality, and then we use that. So let's say we start off with a test equality comparable, and I will replace these tests. So in theory, all the stuff I'm writing should be growing into one big thing. Maybe it goes into multiple functions, however you split that up. But I will actually just retain that and swap some of these things out. So is detected V of, or not is detected of that thing means we don't have that thing. So we can actually nicely report this requirement is not satisfied, and we just print that. We just run it, print it, return false, so we have a failed test case. That is simple and straightforward. We could do a little bit better, and we could actually go and say, well, equality and inequality are actually symmetric. If somebody went ahead and implemented inequality, we can just go and say, here's the implementation, which you can just cut and paste. This is a little bit naive. If a little bit more care is taken so that you can actually work out how the type name is spelled, you could, of course, use type ID .name, but this gives you a funny type. This is not really useful, but you could print a type over there. This is just not fitting on the slide. There's nothing magic over there. So you can just suggest an implementation. Really easy. And then we start doing semantic tests. Now, one thing to pay attention when doing semantic tests, I basically blended them out. I just have the use of the equality operator over here. This would be problematic because that fails to compile if the first operation doesn't exist. Now, if the operation doesn't exist, well, if the operation doesn't exist, we never go on to the second branch. So the obvious fix to that is we make the if constexpr. So now we have that. Unfortunately, that means you somewhat need to nest these guys. You cannot just have if this, and then if this, because the else branch actually is semantically different. So you actually need to put that into the else branch, because the constexpr if says, if this condition is not true, this code is not looked at all, which is what we actually need over here. So just having this constexpr and then having the code outside the else branch does not work. Now, a semantic test on these things. Over here, the EqualityComparable probably needs a little bit odd arguments. For example, using an initializer list, the idea is you would basically provide a sequence of equal values. So the outer initializer list is always a different value, but the inner initializer list is equal values. Examples would be if maybe you implement something crazy, which I contemplate doing, and a decimal floating point. Decimal floating point actually has two different representations of 0. So you want to verify that +0 and -0 are the same. So you would have +0, -0, and then the next thing would be whatever 1 and 1.0. They also have different representations. So some things may be equal, although they represent it differently. So you would test equality, and then you would test things like transitivity and symmetry with things which are actually not equal. Actually symmetry you also want to test with things which are equal. So this is why this actually takes an initializer list of an initializer list, which makes the syntax slightly annoying, but I think all in all that can be made to work. So this would just say, well, the simple test, if x is not equal to x, it's not reflexive, so we have an error. So we just return that, we report that, return that. Obviously, a real version thereof may have extra parameters, and instead of writing to cout or cr, it would write to a specified stream or whatever. But this is kind of messing about making the test environment nice rather than the actual concept of testing. Okay, then other semantic tests. Well, we have constexpr equality, constexpr inequality. So we do both branches. That is relatively simple, straightforward. And then we would also do all the semantic tests across these things. Going on from there, I talked about iterators before. Now, I could show how to do something like, say, a forward iterator. Input iterators are slightly problematic to test, or output iterators, because the moment you move off one, it kind of changes. So I haven't quite figured out how to test these necessarily, but a forward iterator and random access iterator also are entirely definable. Now, forward iterator unfortunately looks kind of weird. It has lots of, basically, this is all there is in the proposed standard. It delegates to, well, I have to be an input iterator. The category is forward iterator, has to be incrementable and sentinel. And then it just delegates to those. And those all delegate somewhere else. So it's actually not a really nice and super readable concept. There's a hierarchy of these guys to find, and actually to test it, things like whatever copyable comes in via semi-regular, and all of these things need to be tested. So this is just, from my point of view, it's just too much fuffing about. So I just talk about bidirectional iterator, which is really simple. This is actually the complete version of how the bidirectional iterator looks in the ranges proposal. The idea is it has to do everything forward iterator does, nothing new over here. Then it has to be derived from bidirectional iterator, and then we have two require clauses. Reasonably simple. It says, all right, we need to return that, and we need to, well, an L value. And there's actually more constraints. There's actually an axiom which says that the pre-increment iterator does return, there's an ampersand missing, does return the address of the object itself. So there's an ampersand missing right there. Sorry, I didn't test the non-testable things. Because it's just text, right? It's kind of, you cannot just pass it in a compiler and see whether it compiles. but it can be turned into a test. And then it says a number of other things. Why does it say that? The next test is also rubbish. The next test should have, is it true? Bool equals A is, oh no, that's not rubbish. Actually, A minus minus, if I call the post-decrement, it should still be the same value. It should return the same value, but A itself is actually modified. So the return value is the same as it was before. And then we have the other guy. If you're on the same position, we decrement both objects. Once is pre and once is post increment. We should get the same thing. And the other guy is going forward and back, or backward and forward. So to basically say these are the requirements to what bidirectional iterators say. So these are the axioms.
But if you are at the end, then some of the expressions will not.
Yes. Obviously, these expressions as written over here assume that you have something in front of A and something behind B, so that you can actually write that. However, in a semantic point of view, well, this is what they're meant to be unless you have the conditional things. In an actual test, you would actually go and say, well, if I get these guys and I need to have equality operations between those before I can figure out whether they are actually the same or not. Otherwise, I cannot test it. And I think I have that actually implemented, so I can show that later. That does work. So basically, it's a little bit more fuffing about than just turning that into code. You need to determine some of the constraints, and there are a few more requirements around. Like, for example, to actually test these things, you actually also need to make sure that you can copy the objects to start with, for example. Okay, so concrete check over here for these guys. We have actually seen how same is implemented before. Requires I++. All you do is write these things. Probably you would write a message, okay, this guy is not available, this guy is not available. But I think everybody knows how to use I/O streams on that level. So the post-decrement test, for example, could also be written to say, well, if I've detected a pre-decrement, sure, and a post-decrement, then I can actually use this implementation. So you can actually suggest implementations. Obviously, some people might go and say, oh, that's not the way to do it. You actually want to do a CRTP thingy where you basically just define a minimal set of operations. Sure, if you have that, suggest that instead. And then people could just go and say, implement that. Using the detection idiom and/or concepts, I could imagine that CRTP could also become better because you basically define, let's say, all the container interface in a CRTP interface. You call that, and then you detect which of the operations are available in the actual class you specify, and you only provide default implementations of those which do not exist. So you can actually start off as, in the beginning, insert. You base everything based on insert, and once you have implemented pushback, it immediately picks up, oh, I got pushback, so I don't define a CRTP version of pushback. So this makes these things somewhat nicer. And then for a decrement test, for example, to test that both of these objects, if they start out at the beginning, you pre-decrement, post-decrement, you first need to check, well, are they equal? Are they copy constructible? Are they does pre-decrement exist? Post-decrement exist? And if so, then we can actually test that. Now, we could actually test a little bit more in that context. So there's an if statement which says, well, it's just one. But we could actually also try to see whether it actually does something. Because the previous test, if we just do that, if I implement minus minus in both cases to just do nothing, then return the correct object, this test passes. But we could actually do somewhat better and say, well, let's try to increment, or in this case, decrement up to 1,000 times. If I then have reached the begin, I'm okay. Otherwise, probably nothing happened. So you need a little bit of the fuffing around, otherwise you may have an infinite loop, and we don't want to have those either in a test. And then, well, obviously this test alone doesn't quite do the right thing. That would actually be a return true at the end. you also need to figure out that you didn't drop off early, so you actually have reached the end, so relatively straightforward. And then, what is that guy giving? Oh, this is the example of testing. Well, if I have a pre-decrement and I have equality, I can actually test whether the correct object is returned from the post-decrement operation. This is all that does. It takes first the address of end, and then it decrements end and verifies that the decremented version of end returns the address. Interestingly enough, it's relatively hard to test the test over here, because in a decrement operation, most likely you just return the object. Returning something else, you need to have something you can reference. Obviously, you can return this plus 1 and you reference that, which is kind of undefined behavior on many levels, but the test would pick that up at least. Okay. With that, I have a little bit of a demo. I hope that makes some sense to basically just see how that feels. If I can get out of that. And over here, unfortunately, I don't see the code over there, so it may be a little bit interesting of typing. This is basically the idea. We have already set up a forward iterator. This is all there, and we test that. And the entire idea is let's go and say instead of forward iterator over here, we actually well, let's go. Sorry, where's that? It's over here. So if I build that, it just says, yeah, everything's okay. There's no report coming out. If I then go and test that, for example, and go and say, well, I have a forward iterator, so I want to change that into a bidirectional iterator, then immediately, if I get to the test and I compile that, it actually says, hopefully, that, oh, right, iterator category is not the right one. I don't have the corresponding operators, so it actually guides me to say, all right, I need to implement those things. The easiest one to get rid of, obviously, is, oops, sorry. Help. Oh. The easiest one to get rid of is over here. We just fix that. Just reasonably change. Let's go by directional iterators. We get rid of that. And let's just start off as implementing our operators. So we go and say we write our increment operator and, decrement operator, and I'm really lazy. All I do is this. So now the test immediately goes and say, oh, cool. It seems pre-decrement doesn't reach the beginning, so it doesn't do anything. It picked up on that. So I need to do something, okay? It also, post-decrement is not detected, so it actually tells me, unfortunately, a little bit later, but that is something to be sorted out from the test system to say, here's how you can actually implement that. So we could actually copy and paste that if I knew where the mouse is. Where does the mouse go out? There. So we could actually just copy and paste the code and say, all right, this is how we want to implement our operator over here. And then go.
Looks like you have a copy-paste error in your copy-paste code.
I have a
Because it's doing plus plus.
It looks like increment.
Oh, for fuck's sake. And I'm really objecting to copy and paste. Surely I have not copy and pasted that code. Okay. So okay. So you need to test the tests, yes. Testing tests, okay. But if everything goes well, we actually have now implemented one of the operators, and actually I did do more things wrong. Oh, I know what I did wrong. I didn't update the name over here, unfortunately. So more things to work on, but conceptually, I think everybody can see that that works, right? No, what did I do now?
You changed the wrong thing.
Oh God. Yeah. This is getting nervous and typing. Some people know that I do that on a regular basis, and I'm not better than either. So.
You need to take them as well.
well, I need to decrement, but it tells me that it doesn't reach these things, right? So I actually need to do some more work. So let's go over here and let's say, I just implement the simple way over here, just go and say minus minus this pointer Dietmar. And if everything goes well, then eventually it all just works. Oh, the return type, exactly, right? So, but it keeps telling me, right? And these are things you need to look up and figure out, and over here it just tells me. So I actually like that experience, that I get all these things wrong. I understand that if I had Marshall always with me, he would tell me that anyway, but I don't. I guess Marshall would be upset about if I try to use him like that.
Being made obsolete.
Yes. Well, incidentally, right? Okay, done. No. Thanks. Now, Marshall is worried about getting obsoleted. Please, everybody who thinks that was a good thing, tell Marshall, implement these tests so he doesn't get obsoleted, right? This kind of his not so good colleagues from maybe alternative standard libraries who don't provide these tests may get obsoleted, right? But we don't want Marshall to be obsoleted. Okay, cool. Anyway, this is getting back to, okay, now I need to find the mouse over here. Getting back to the thing, this is pretty much all I wanted to talk about. So there's plenty of time for questions and comments, if there are any. Oh, no questions. Then we have lots of beer and things. You may get to one of the short talks in one of the other rooms. I don't know when they break exactly. Yes?
I find the presentation very interesting. Is the small sample that you showed us available for download?
Oh, absolutely. Let me go first. Thank you. Right. And by the way, in case you worry why we do that, we are hiring. Right. So, a number of links. So the demo implementation. There's the concepts for the library and the concepts for range STS. So the link is basically my generic attempt to write some of the standard library things. If you look at that thing, all the code is there. It is hideous. It's not cleaned up. And feel free to email me, and I'm happy to send you the links or whatever you need over there. Okay, anything else? Otherwise, thank you very much.